Okay, continuing page 6 of the differential equations packet, we're now actually going to take a look at how do we solve differential equations. And one of the processes that we use is something called separating the variables. And so that's what we're going to take a look at on the next couple of pages. So let's start with what makes a differential equation separable. Basically, if you look up a definition, it would say that a first-order differential equation, that just means we're dealing with dy dx, is an equation of the form which can be factored into a function of y multiplied by a function in x. So you're looking at some function of y times some function of x being multiplied together. And in that case, if we can write a differential equation that way, then we say that that function is separable, which means we can separate the variables. And all that means is we're going to put y on one side and we're going to put x on the other side. We're going to literally separate the variables. Now, a solution of a differential equation is a differentiable function. Differential implies continuity, so we want to make sure that's going to come back as we talk about the domain of this function. On an open interval that contains the value of the independent variable in the initial condition. So let me give you 5 steps for solving a differential equation. Now, if you were to take a look at a free response question on an AP test, they would give you, if you look at the solution guide for that FRQ, they would give you these 5 steps. The first step when you are solving a differential equation must be to separate the variables. Okay, so again, that means put the x's on one side, put the y's on the other side. After you do that, you're going to antiderive or integrate. Antiderive both sides. Okay. Do not forget, this is that third step, do not forget the constant plus c. Then what we're going to do is you'll oftentimes be given some sort of initial condition. So you're going to use the initial condition to find this plus c value. And then once you find that constant, we're going to go ahead and solve that equation for y. In this one here, we do have to be very careful that we take into account this initial condition, and you'll see in the coming examples how that works. So let's take a look at this first equation here. I'm going to use this white paper because we need a little more room than there's allowed. It says when finding the solution to a differential equation, it's important to also identify the domain on which the solution is valid. The domain will be an open interval which contains the point given in the initial condition. So let's take a look. Consider the differential equation dy dx is equal to x squared times y squared. So we can see, first of all, because this is a product of a function in x and a function in y, this is going to be separable. It says find y is equal to f of x, the particular solution to the differential equation, with the initial condition that f of 0 is 1. That is, it contains the point 0, 1. State the domain of the function. Okay. So let's take a look at this. So the first thing we're going to need to do is separate these variables. So we're going to go ahead and we'll multiply both sides by the dx, thereby canceling the dx. We're going to divide both sides by y squared, bringing the y over to the left side. So again, when I multiply by dx, that gets rid of the dx from the left side. When we divide by y squared, that means I have a 1 over y squared here. On the right side, we still have our x squared, and we have multiplied that by dx. If you choose to, we can write it again as y to the negative 2 dy is equal to x squared dx. At this point, we're going to integrate both sides. So I get y to the negative 1 over negative 1 equals x cubed over 3 plus c. So simplifying this, I get negative 1 over y is equal to x cubed over 3 plus c. At this point in time, we're going to go ahead and find our c value. So I'm just going to come up here. I'll continue up here by substituting when x is 0 and y is 1. So I get negative 1 over 1 is equal to 0 cubed over 3 plus c. 0 cubed is 0, divided by 3 is 0. So I get c on the right-hand side, and we get negative 1 on the left-hand side. So c is equal to negative 1. So now my function becomes negative 1 over y equals x cubed over 3 minus 1. Now from here, there's a few different ways you can go. I would say this is purely preference. What I like to do is, if I have a y in the denominator and a 1 in the numerator, if I just reciprocate this fraction, y is up top and 1's on the bottom. That's exactly what I'd like to do. The problem is, if you reciprocate the left side, I have to reciprocate the entire right side, which is going to be a problem in its current state. So I can fix that by, let me put that 1 over y, by going ahead and thinking of 1 as 3 over 3, and then combining these two terms to make it x cubed minus 3 over 3. Now the entire right side is a fraction. So if I reciprocate the left side, I get negative y, and if I reciprocate the right side, I get 3 over x cubed minus 3. Now to finish solving, we just multiply both sides by negative 1, so I get y is equal to negative 3 over x cubed minus 3. So that is our function that has as its derivative dy dx is equal to x squared y squared. Now we could derive this in a different way and get a different answer, but they would be equal. They would be equivalent expressions or equivalent equations. So let's take a look at the domain. First of all, this is a rational function. A rational function has its domain everywhere except for whatever would make this denominator 0. So off here to the side, x cubed minus 3 equals 0 when x cubed equals 3, which happens when x is the cube root of 3. So if we go back to just regular old algebra 2, we would say the domain of this function would be all real numbers except the cube root of 3. Or we would say that the domain was negative infinity up to the cube root of 3 and the interval cube root of 3 to infinity. However, notice this is not a continuous function. This has a discontinuity at the cube root of negative 3. So therefore, our derivative, we would have to adjust for that because, again, this is differentiable, which means, this is a derivative. So this means our function is differentiable, which means it must be continuous. So we need to look and say which of these intervals contains this initial value of 0, 1. And the one that contains 0 is this interval right here. So our domain for this function is going to be negative infinity, or the interval from negative infinity to the cube root of 3.